All right, let's go over our test. This wasn't the sample test, it was the test. And for those of you who may not have been in class for this test but are watching this video, what we did in class is I had a couple students help me, and we hung on the whiteboard rubber bands linked together and then clipped to a paper cup. And I had them give me 10 pennies. We put them in the cup and we measured from there to the top of the cup, and it was 22.5, and this was in inches, and this was the number of pennies. Okay, so that's how we collected the data. So the first thing we need to do is you're supposed to say, what does the independent variable measure? The independent variable measures number of pennies in cup, and the dependent variable measures the length in inches of the rubber bands. Okay? Then it says we graph the data, including labeling the axis. So now this is going to be a little hard to show in the video because I'm going to lose it, but I want to use most of my distance across, so I'm going to draw a line here. And the independent variable gets up to 100, so 50 is about here, so maybe I do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's too far. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That allows me to use most of the graph. Now vertically, we have 22 to 33. I'd like to spread that out, so I'm going to leave some out here so I can spread out what we have. So I'm going to do, let's say 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I'm going to be a little bit off here. I probably should have started one. Well, that should be good enough to get most of the data. I'm going to stay with that. So this is the length, and we're supposed to label this length of rubber bands in inches, and this is number of pennies in cup. Okay, the units are just number of them. Okay, so let's graph. So first is 10, 22.5, 10, 22. I probably should, let me fix this. 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Now I should be able to get almost everything on there. So first one, 10, 22, that's 23, 22, 22.5. 2023. 2023. 30, 23.5. 40, 24.5. 50, 25.5. 60, 26.5. 70, 27.75. 80, 29.5. 90 is 31. And 100 is 32 is here, 33, it's about there. A little bit off. Looks like a little bit of a curve in it, but we could draw a fairly straight line through this. So I'm going to draw something that looks like this. This is going to be my line. And determine the slope. So it's close to this point and close to that point. So I have from my line 20, 23. And this point is 55, 27. Now, if you're doing this in class or doing it on yours, you might choose something a little different, so have a little different values, but determine the slope. So the rise went from 23 to 27, so it rose 4 inches, because this is inches, for 20 to 55, that's 35 pennies. Now I could take my calculator out, if I can find it. Where did I put it? There it is. And get a decimal value for this. So I have 4 divided by 35. 0.114. It's approximately 0.114 inches per penny. So it means that the rubber band gets 0.114 inches longer for each penny added to the cup. Y-intercept. 22, looks like it's about 21. 21 inches. And the meaning of this is length of rubber bands with no pennies in the cup. Okay, so that's the first page of your test that we had in class. Okay, second page. Given the data in problem 1, use technology to determine the best fit line. So now I've got to get my data back out here again and put it into either Desmos or in this calculator. So I'm going to go Stat on a calculator, Edit, and I'm going to go to List 1, and I need to put 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, and for the links, they were 22.5, 23, 23.5, 24.5, 25.5, 26.5, 27.75, 29.5, 31, 33. Okay, so I could look at the graph on this. Let's see if I clear that and make sure plot 1 is on. Second stat plot, plot 1 on using list 1 and list 2. It's going to put little crosses, so then I can go zoom, stat. There's the picture of it. It doesn't look like a straight line, but so be it. Okay, now to have the calculator find the equation, I go to Stat, Calculate the linear regression model, linreg, where A is the slope and B is the y-intercept. Hopefully we get numbers close to that number and that number. Okay, so I'm going to go there, and that says I'm going to use list 1 and list 2. And just to help me see it, so it'll graph that, I'm going to say vars, y vars, function y1. So it's going to put store the equation, the regression equation in y1. That's under the y equals, so that it'll graph it. So press enter and enter, and it picked a slope of 1.159, 1.16. A little bit more change per penny. It has a y-intercept of 20.3 inches. We said 21, so that's close too. So let's go over here. The line of best fit is y equal 0.115x plus 20.3. That's in inches, and this is inches per penny. And the correlation, how well did it fit? It fit pretty good. It's 0.98. Now, just a note, if I were to see data that looked curved, there's where the line went. If I had data that curved like this, I might try using a quadratic or some other regression model instead of a linear, because this looks like it definitely curves. Okay? All right, so that's number 2 and 3. Number 4. Okay, so if it's going to be increasing or decreasing or constant depends on the slope. The slope is the number times x. That's a positive 4. So this one is increasing. This one, there's no x, so it's a constant. Next one, it's negative 5x, so it's decreasing. Now we have to write the equation through these points. So I need the slope, which is change in y, 3 to 5, it goes up 2. change in x. Minus 2 to minus 3 is minus 1. So the slope is negative 2. So my equation is going to be y equals negative 2 times x plus some b. And I got to figure that out. And I'm going to put negative 2 in for the x. So I'm going to have negative 2 times negative 2, which is 4 plus b. 4 plus b has to equal the y, which was supposed to be 3. So if I subtract 4, I get negative 1 for b. Now let's try using the other point. So I have negative 2 times negative 3, which is negative 6, and I'm supposed to equal 5. So if I add, so negative 3, that's plus 6. Negative 2 times negative 3 is plus 6. So if I subtract 6, I get negative 1 again. And that's a good way to check and make sure you've done things correctly. If you put that in for the x, and you're supposed to get that, and it should work. But if I put that in for x, you get this, and 5, the same number should work here as it does there for b. In this case, it was negative 1. So I found the equation. Now we need the linear model for 1950 being 0, 1980, which is 30 years later. The population was 1,500 in 1950 and 2,300 in 1980. Oh. So I need to do the slope. Change in y went from 1,500 to 2,300. That's 800 more people over 30 years. So 800 divided by 30 is about a little over 26 people, 26 and 2/3 people, or 26.66 more people. It's plus, so it's more people per year. That's the slope. So the equation would be y equals 26.2/3 times the year times t would give me the population as a function of t. Plus a y-intercept, which means at 0 it was 1,500 plus 1,500. So now we can take this and plug in 2015, not that number, but how many years past 1950 is that? So that's 65 more years than 1950. So we put 65 in for t. So I'm going to write this number times 65 plus 1,500. And it says the population would grow to 3,233. 3,233 and a third people, but we'll round up. That's the predicted population in 2015. We got that by doing 26 and 2/3 times 65 years later plus the starting amount of 1,500 people.